You land at JFK, you grab your bags, and you just push a button on your phone.
Right, and you expect it to just work.
Exactly. I mean, a little digital car crawls across the screen, and maybe 3 minutes later, a real car pulls up right to the curb. It feels completely like magic.
Yeah, we totally love the illusion of simplicity. I mean, we want the result without seeing any of the friction behind it.
But underneath that button, underneath that seamless UI, is just uh, a hyper-constrained mathematical war zone.
Oh, a war zone is the perfect word for it. Because to actually make that match happen in real time, pairing a specific driver to your exact location with thousands of other moving variables, that requires a staggering amount of computational brute force.
And that war zone is our destination for today's deep dive. We've managed to get our hands on a really incredible source. It's a highly detailed, intensely strategic preparation document.
Yeah, this is basically an insider's blueprint.
It really is. It's for a 60-minute operations research senior scientist interview at Uber Mobility, specifically for their airport science team.
Which is a phenomenally competitive role.
Right, so our mission today is to decode the hidden engine that runs modern logistics for you, from grounding flights to routing that car to your terminal. We want to explore exactly how a top-tier expert prepares to prove their worth.
And keep in mind, this isn't just a test of writing a few lines of code.
Right, it's not just a programming quiz.
No, not at all. This role demands pure mathematical problem solving, whiteboard modeling, and really razor-sharp business intuition.
The part that really stuck with me, though, is that the candidate who wrote this prep doc already holds a PhD in operations research.
Yeah, they aren't a novice.
Exactly. They have over 6 years of intense, real-world engineering experience. But they still rely on this meticulous, step-by-step checklist just to survive the 60-minute gauntlet.
Because past credentials just get you in the room.
Yeah.
The tech industry at this level, it operates on a completely prove-it-right-now mentality.
So they have to perform on demand.
Right. Before a company like Uber trusts someone to optimize their global network, that person has to demonstrate they can tame real-world chaos on the spot.
So how do you actually prove you can tame chaos?
Well, the first 10 minutes are dedicated to past projects. The prep document outlines these highly rehearsed, tight, 3-minute pitches.
Yeah, they even have 1-minute elevator versions ready to go.
Yeah.
And their primary pitch is this project called Wheels Up, dealing with aircraft on ground or AOG emergencies.
Which is a nightmare scenario. When a commercial flight is grounded due to a mechanical failure or weather, it triggers absolute logistical chaos.
Because an aircraft sitting on the tarmac is just bleeding money by the second, right?
Exactly. And it causes cascading delays across the entire network. So the candidate solution here was to use something called a mixed integer programming formulation, or a MIP.
A MIP, right. And they use this to reassign crews and aircraft in real time.
Yes. They have to balance FAA duty limits, crew compatibility, and empty flights, which they call deadhead miles.
And the massive win here, like the headline achievement, is that they took the system's decision-making time from 10 seconds down to about 1 second.
Which is huge.
I mean, to a casual observer, a 9-second improvement might not sound like a big deal.
Oh, but in computing terms, that is a massive, massive leap. It's the difference between a system that functions and a system that just collapses under its own weight.
It honestly sounds like playing a game of 3D Tetris, but the falling blocks are angry passengers.
Yes. And you're playing against ticking regulatory clocks.
Right. But how did they actually get it down to 1 second?
Well, they built a stored procedure pre-filter and tuned a mathematical solver called Gurobi.
So basically, they built a bouncer for the algorithm. Like, they filtered out the obvious nose-like, matching a pilot to a plane they aren't even certified to fly before the heavy math even started.
Exactly. You shrink the maze before you ask the computer to run through it. And that perfectly maps to Uber's job description, which asks for the ability to decide which earners to approach and when.
But this is where the strategy gets a little counterintuitive to me. They have this backup project from a company called Quincus, routing a mixed fleet of bikes, vans, and trucks for specialized items.
Right, like cold chain medical supplies or oversized packages.
Yeah. But for this one problem, the candidate prepped 2 completely different mathematical solutions to present.
One classical, one AI.
Right. One is a classical integer programming approach, and the other is an AI-driven reinforcement learning approach, a deep Q network. Doesn't pitching 2 different solutions make them look indecisive?
I mean, that assumption makes sense on the surface. But in advanced operations research, there's rarely one perfect tool. Every algorithm is a trade-off.
So it's about showing flexibility.
Exactly.
Hmm.
By presenting both, they show they understand the trade-offs. The classical integer programming offers mathematical guarantees. You can mathematically prove it's the absolute optimal path.
But I'm guessing the catch is the speed.
Yeah, computational speed and rigidity. If an accident happens while the vans are en route, recalculating that perfect path from scratch just takes way too long.
So that's where the deep Q network, the DQN, comes in. How does that AI approach differ?
Well, reinforcement learning is fundamentally different. It's not looking for a strict mathematical proof. It learns by trial and error through a reward system.
Kind of like training a dog.
Exactly like that. The algorithm takes an action, like sending a bike down a street. If it's fast, it gets a digital reward. If it gets stuck in traffic, it gets penalized.
So over millions of simulations, it builds up a sort of intuition, a learned policy.
Right. It learns the fastest routes without needing to calculate the entire city map from scratch every single time. It scales incredibly well for massive real-time problems.
But it lacks the guarantee, right?
Yeah, it might give you a route that is 98% efficient instead of 100%, but it gives it to you instantly.
Showing you can pivot between those two things is a massive signal of maturity for an Uber interview.
Completely. It shows they can handle the uncertainty of an airport queue.
So, past projects are out of the way. The candidate has proved they can handle chaos. Now, the interview transitions to the ultimate unknown, the 40-minute whiteboard case study.
The deep end of the pool.
Yeah, they are going to be handed a massive surprise problem on the spot. And to survive this, the prep doc outlines a really strict 5-step architectural template.
They definitely do not just wing it.
No, the steps are clarify, identify, and model, solve, productionize, and business connection. And I really want to look at that first step, clarify.
It's the iron rule of the interview.
The document explicitly states that starting to solve the problem immediately without clarifying is the #1 reason candidates fail.
It's the most common trap for brilliant people. You get handed a complex problem, and your instinct is to immediately show off how smart you are by writing out a solution.
But you don't even know the actual boundaries of the problem yet.
Exactly. The problem as presented is almost never the complete picture. You have to ask about scale, constraints, the core objective.
Like, is this a real-time process or a batch process?
Right, because if you design this elegant algorithm, assuming you have 5 minutes to run a batch of data, but the business actually needs a real-time match in 50 milliseconds.
Then your brilliant algorithm is totally useless.
Utterly useless. Defining the boundaries of the sandbox is way more important than the castle you build inside it.
Which brings us to step 2, the modeling. And I have to say, reading this part of the document was genuinely intimidating.
Did a lot of math.
It is. The expectation is that a human being will just write out a complex math formula decision, variables, constraints, objectives on a whiteboard from memory under intense pressure.
Yeah, they are literally practicing memorizing things, like a bipartite assignment, MIP.
Is that level of raw memorization really necessary? It feels like they're testing a calculator, not a human.
Well, the memorization itself isn't the ultimate goal. The whiteboard math is simply table stakes.
Just to prove you know the vocabulary.
Right. Anyone can look up a formula. The real differentiator is step 4, productionizing.
Taking the math from the whiteboard to the actual server rack?
Exactly. A formula on a whiteboard doesn't experience server latency. It doesn't crash when 1,000 people land at an airport and open the Uber app at the exact same millisecond.
So knowing the math isn't enough.
No, you have to engineer around reality.
Yeah.
Like the candidate notes they need to discuss warm starting a solver.
Okay, what does warm starting actually mean in this context?
So, complex algorithms need a starting point to begin searching for the best answer. If you drop it into massive data cold, it wastes precious time just wandering around.
Trying to find its bearings.
Right. A warm start means you inject a highly educated initial guess into the system based on historical data. You give the algorithm a head start.
So it finds the optimal answer way faster. That makes total sense. But to pull off this kind of architectural thinking on the fly, the candidate has this huge mental library.
The theory versus reality matrix.
Yes, the arsenal of mathematical tools they are cramming the night before. I mean, the breadth of knowledge here is staggering. Linear programming, integer programming, network flows, dynamic planning.
It's basically an entire PhD on one page.
Seriously, how does anyone know which of these highly complex tools to actually use? Is it just throwing high-level math at the wall and seeing what sticks?
No, it all loops back to those constraints they identified in step 1. You choose the tool based on the structural bones of the physical problem.
Okay, give me an example, like linear programming. The doc mentions understanding the simplex method versus interior point methods.
Sure. Imagine a 3D gemstone, like a diamond. Every flat edge and sharp corner represents a set of constraints: driver availability, traffic, wait times.
Okay, I'm picturing a diamond.
The optimal solution always lives on one of the outer corners of that shape. The simplex method basically walks along the outside edges, moving from corner to corner until it finds the highest peak of efficiency.
Oh, so it just traces the perimeter to find the best spot?
Exactly. But that only works for smaller operations.
Yeah.
What if Uber is trying to optimize the entire city of London at rush hour?
Then that diamond has millions of edges.
Right. Walking the perimeter would take forever. So the candidate knows they must switch to an interior point method.
How does that one work?
It mathematically drills a tunnel straight through the middle of the shape, bypassing the edges completely to get to the optimal point faster.
Wow, okay. So the sheer scale of the problem forces the shift in the mathematical tool.
Scale dictates the approach, absolutely.
What about when the problem involves physical routing? Like the document mentions combinatorial routing and network flow problems, specifically Dijkstra's algorithm.
Dijkstra's is a classic routing tool. It calculates the cost in distance or time of every possible street connection expanding outward from your location until it hits the destination.
Like a GPS finding the shortest path.
Right. But it assumes the world is static.
And the real world is definitely not static. Traffic accidents happen, weather changes, physical world uncertainty.
Exactly. You can't use rigid tools like basic Dijkstra's when the environment is shifting. For that, the candidate prepares for dynamic and stochastic planning.
Which they call Markov decision processes, or MDPs. How does an MDP handle unpredictability?
It models a system based on different states and the probability of transitioning between them.
Okay, what's a state?
Say, State A is sunny with light traffic. State B is sudden rain with gridlock. An MDP doesn't just calculate a route, assuming State A lasts forever.
Because it probably won't.
Right. It incorporates the statistical probability that State A shifts to State B in the next 10 minutes. And it calculates a policy that provides the best average outcome across those uncertain futures.
Oh, so it's math designed to actually absorb randomness. That's brilliant.
It anticipates the chaos rather than just reacting to it.
And throughout all of this, the prep doc insists the candidate must constantly talk about big O complexity. What is the practical application of big O here?
Big O is just a way to measure how an algorithm's performance degrades as the amount of data explodes.
Like how it scales.
Yeah. Think of cooking in a restaurant. If a recipe takes 5 minutes for one person, does it take 50 minutes for 10 people? Or can you make all 10 in the same 5 minutes with a bigger pot?
Got it. So if a matching algorithm has terrible big O complexity, it might work perfectly for a small town, but it will literally crash the servers in Manhattan.
Exactly. You have to prove your math won't break the servers.
So they've mapped the constraints, chosen the right algorithm, proved its scales, but all of that wizardry falls flat if they can't translate it into the company's specific business language.
Step 5. You have to speak Uber.
Right. The document is just packed with this mandatory jargon, DAEE, which is their dispatch engine, deadhead, virtual queues for airports, surge pricing.
You have to show you understand their specific ecosystem.
But there is this one psychological tactic in the prep doc that I found incredible. The candidate plans to intentionally volunteer a failed experiment or a challenged assumption to demonstrate, quote, research maturity.
It's a genius move at the senior scientist level.
But isn't it incredibly risky to volunteer a failure during a job interview? I mean, shouldn't you be showing off?
A junior candidate thinks an interview is a performance of flawlessness. But a senior architect proves their value by showing they know exactly where and why the tools break.
Knowing the limits of your tools.
Yes, and the document ties this failure strategy specifically to A/B testing in a ride-sharing environment.
Okay, because traditional user-level A/B testing is like the gold standard for most tech companies, right?
It is, but it often fails catastrophically in matching markets like Uber.
Why A/B testing works for e-commerce, it works for streaming. Why does it break for ride-sharing?
Because of a concept called SUTVA, the stable unit treatment value assumption.
SUTVA, okay, break that down for us.
In a normal A/B test, like on a retail site, if I'm in the experimental group and I see a new buy button, my behavior doesn't affect your experience in the control group.
Right, we're totally isolated.
The assumption of stability holds up. But ride-sharing is a shared ecosystem with finite physical resources, the drivers.
Oh, so if the algorithm gives a driver to me because I'm in the experimental group,
It has literally stolen that driver away from the pool available to you in the control group.
Wow. So the groups end up cannibalizing each other.
The test completely contaminates itself. The control group isn't experiencing the normal network. They're experiencing a network artificially depleted of drivers.
The results of the test are fundamentally lying to you.
That is fascinating. So
Oh.
how do you test anything if traditional A/B testing is lying?
The candidate plans to ask if they use switchback experiments. Instead of splitting users, you alternate the algorithm across entire blocks of time.
Like switching the whole city to algorithm A for 2 hours, then algorithm B for 2 hours.
Exactly. Or they ask about synthetic controls. By discussing this failure, they prove they understand how hard it is to measure objective truth in the physical world.
Which perfectly tees up their final strategic move for the Q&A section. They plan to ask the interviewers about the explore-exploit trade-off.
The ultimate tension in operations research.
Yeah, the tension between long batching windows, which gives the system more data to find a mathematically optimal match, versus writer patience. Because human beings are impatient.
We want that car matched right now, even if it's technically less efficient for the global network.
And that tension is the beating heart of their business model. When a candidate asks that, they aren't interviewing as a mathematician anymore. They're conversing as a business owner.
They know the math serves the user experience. Well, tracking the 60-minute journey has been intense.
It's a real mental decathlon.
It really is. Moving from taming real-time chaos to architecting these massive models under extreme pressure. But beyond all the algorithms and server latency, there's a profound takeaway here for you, the listener.
Absolutely.
The next time you face a complex, overwhelming problem at work or at home, steal this candidate's iron rule. Refuse the urge to start solving it immediately. Step back. Rigorously clarify the constraints, map the scale, and define the true objective first.
Ensure you are actually building a solution for the right sandbox.
Yeah.
Because the math and the tools are all secondary to defining the reality of the problem first.
It really makes you wonder, though. This entire preparation document relies on the power of optimizing for known constraints, right? Travel times, FAA limits, vehicle capacities.
It's deeply, wonderfully logical.
But as these mathematical models increasingly run the physical world around us, from the car you hail to the packages you receive, what happens when algorithms hit the deeply unquantifiable?
Because the physical world is incredibly messy.
Exactly. How do systems built on perfectly logical mathematical constraints survive sudden cultural shifts or mass human irrationality?
Or unprecedented global events.
Right. No historical data or switchback experiment could ever predict a true black swan event. Can you ever truly mathematically optimize for the unknown? Next time you push that button and a car magically appears, ask yourself what kind of underlying chaos that algorithm is barely holding back.